All right, for this problem, it says hydrogen peroxide decomposes according to the equation above. An aqueous solution of hydrogen peroxide that is 6% hydrogen peroxide by mass has a density of 1.03 grams per mol. Calculate each of the following. The original number of moles of hydrogen peroxide in a 125 milliliter sample of 6% hydrogen peroxide solution. So what I did was I first said, okay, how many grams of this solution do I have? Well, I'm going to take 125 and multiply it by the density, which is 1.03 grams per mol. And so that tells me I have 128.75 grams of this solution. Well, only 6% of that mass of the 128 grams is actually hydrogen peroxide. The rest is water. So what I'm going to do is I'm going to multiply the mass of the total solution by 0.06 because I need to make the percent a decimal, and I find out that I have 7.73 grams of hydrogen peroxide. Okay? Then it's not asking for grams of hydrogen peroxide, it's actually asking for the number of moles. So I need to take 7.73 and divide it by the molar mass of hydrogen peroxide. So the answer I get is 0.227 moles. So you got 1 point for determining the mass of hydrogen peroxide. Remember, you don't have to put an equal sign. You could have kept going, and they did that. I covered it up, but that's how they did it. That's fine, as long as you're showing the work necessary to get into moles. 1 point for, so 1 point for the mass of the solution, so the 128 grams, 1 point for the mass of hydrogen peroxide, the 7.73, and then 1 point for the number of moles. So that was a whole lot of points for one little problem. Then it says the number of moles of oxygen that are produced when all the hydrogen peroxide in the 125 ml sample decomposes. Well, I need to use the my mole-to-mole ratio because I know 0.227 moles of hydrogen peroxide are there. I'm going to convert it into moles of oxygen. It's a 1:2 ratio, so I get 0.114 moles of oxygen. So you get 1 point for that. Keep in mind, if your answer from AI was wrong, as long as you use your wrong answer from AI in II, then you'll get that point. All right, so big idea for material. It gives me two graphs. It says write the rate law for the reaction, justify your answer. So remember, just as a quick refresher, if your graph for concentration versus time is linear, then you know that your reaction is zero order. If your graph for ln versus time is linear and with a negative slope, then it is first order. And if your graph for 1 over concentration versus time is linear with a positive slope, you know that it's second order. Okay? So it says write the rate law for the reaction. Okay? So it's going to be rate equals K times the concentration of H2O2. And that's it because it's first order with respect to hydrogen peroxide. Then it says justify your answer. So you need to say, since the graph of ln of concentration versus time is linear with a negative slope, we know that it is first order. So you got 1 point for the correct rate law and 1 point for the correct explanation. So for II, it says determine the half-life of the reaction. So there are two different ways you can do that. The first way, which I automatically thought about, was the fact that I just need to figure out, looking at the concentration versus time, when will half of my reactant have decomposed. So if you look, when I go from 1, I need to go to 0.5, and that's right around, I want to say, I don't know, 650. They say 650. Fine. Notice you get a point for saying it's between either 600 to all the way to 700 minutes. Or you could look at the other graph and say, okay, since I know this is a first order reaction, I know that my half-life equals 0.693 divided by K. Well, to determine your K, you just need to find the slope of that line. So once you determine that slope, and then you can find your half-life. I think that's harder. Honestly, I think it's much easier to determine your half-life by just looking at the first graph. Okay. In III, it says calculate the value of the rate constant K. Include appropriate units in your answer. Okay. So what you can do, again, there are two ways to do this. First of all, you can say, all right, I know what my half-life is. We said it was, let's say, for example, 650. Plug it into your equation and you can get your K, which in this case would be 1.1 times 10 to the negative third. Now, please, 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 please be careful with your units for K. The overall order is first order for this reaction, which means since I want my rate to be molar per minute, I only have molar right now on my right-hand side because I only have the concentration of H2O2, right? It's not squared. So the units for this would just be minutes to the negative 1. If it were second order, then I'd have molars squared, and I'd be wanting to get rid of one of those molars in order to get into molar per minute. And so my units would be molar to the negative 1, minutes to the negative 1. Notice they always give 1 point just for the units. If you have no idea what's going on, but you can put the units for your K, please write your answer to the best of your ability and include units. Do not forget your units. So this is worth 2 points. So you could either do it that way, or just like I'd said before, you can find the slope of this graph, and then that would be your K. All right. In IV, it says determine the concentration of H2O2 after 2,000 minutes elapse from the time the reaction began. Okay. So again, 2,000 minutes. So you got to look on the graph and figure out what that would be. And so it's approximately, if you look back at the graph, 2,000 minutes, it's going to be approximately 0.12 mole. The other thing that you could also have done is plugged in the values for your to the first order equation. So ln of AT equals negative KT plus ln of A naught. That being said, ln of AT, you'll be solving for ln of AT. Ln of A naught is just going to be 0. Okay, so you'll have to figure out you got your K before. You have 2,000 minutes, and so you can actually calculate AT if you want to do it that way. Or you could just use your graph.